How many bonds does nitrogen like to form? Just remember your favorite nitrogen compound, ammonia. What's the formula for ammonia? NH3, possibly 3. Or we say group number 5, 5 valence electrons, once an octet. Or think nitride, the ion, from Chem 1 would be N3 minus. 3 protons hooking up. So here is our ammonia, NH3. Nice, no charge. Here's the Roman numeral 5. Here's 2 minus non-bonding. There's 2 of them. 2, 4, 6 bonding electrons. I get to count half of those. Half of 6 is 3. Negative 3 and negative 2 is a negative 5. Summed with a positive 5 is 0. And then, of course, the ammonium cation. You got that memorized because it's a polyatomic ion you have to deal with in Chem 1. NH4 plus charge. Where did the plus charge come from? Okay. Here's our group number. 0 non-bonding electrons around this. 2, 4, 6, 8. Half of 8 is 5. 5 summed with a negative 4 gives you positive 1. So we have an organic reagent called sodium amide. Put this up with a sodium, so it's like NaNH2. And it's a nice, strong base. Wants an electron. Let's make sure we know how to work our formal charge. Still see Roman numeral 5 above carbon on the periodic table. 2, 4 non-bonding electrons. 2, 4 bonding electrons. Half of those is 2. So I have 5 summed with a negative 6. Should get me to negative 1. All right, any questions on these? What do I do next? Carbon, the star of organic chemistry. And some nice organic chemistry things here. If these are hydrogens, I didn't draw what was bonded there, but it's our usual alkane. Talk about those in a little bit. Roman numeral 4 above carbon on the periodic table. 0 non-bonding electrons. There are 2, 4, 6, 8 bonding electrons. We get to count half of those. So 4 minus 4 is 0. All right, so here's a species. If we imagine pulling a hydrogen off, if one of these was a hydrogen, well, just scratch that. Just if we have carbon with 3 bonds and nothing else going on, we're going to go 4 minus half of these, 2, 4, 6, and come up with positive 1. So we call this thing a carbocation. And students always make me crack up. They sometimes say carbocation, which sounds like a process. All right, so here we have a species. It's called a carbanion. Anion, negative charge. Cation, positive charge. What's going on? 2 non-bonding electrons, 2, 4, 6 bonding electrons. Plug that in there. We're going to have 4 summed with a negative 5 gets us to negative 1. So that is how we do formal charge. And you can see the formal charge in play right now. Look, this carbon has 3 bonds. You learned it normally wants 4. There's no non-bonding pairs around there, so it's going to have that positive charge. And so we like to draw resonant forms. What is a resonant form? When 2 or more Lewis structures are possible, differing only in the placement of electrons, we call them resonance forms. The actual molecule is said to be a resonance hybrid. So here we see our formal charge in action, and we also see our curved arrow formalism. I take and start an arrow above the electrons and draw it towards an atom. I'm playing by the rules. And look, that now puts 4 bonds on carbon. That means it's not going to have formal charge. And look, nitrogen likes to have 3 bonds. Now it has 4. If I do the formal charge things, it's going to have a positive charge. So we say this thing in nature would exist as this, with a partial positive charge on each one of those atoms. And probably there's going to be a little more positive charge on carbon than nitrogen, because I'm going to say nitrogen's a little more electronegative. It's not going to want the positive charge as badly as carbon. Not to say they both don't want the positive charge, but they're stuck with it. So resonance structures differ only by the placement of electrons. All right, here looks like formaldehyde, and then we don't see any charge. Oxygen has 2 bonds. That's what it likes. Carbon has 1, 4. Hydrogen only forms 1 bond because it obeys the rule of 2. I can start a little arrow here and push those electrons up onto oxygen. That's a skill you're going to learn here. All right, so that does away with that bond. I had a hard time getting the computer to draw a line coming exactly from those bonds. And so now we have oxygen with 1 bond and 3 lone pairs. Plug that into the formal charge formula, and you're going to get a negative charge. And we just saw that here's this carbocation, and oxygen is more electronegative than carbon. So that gives this molecule a dipole moment, and so we can think of oxygen having a partial negative charge and carbon having a partial positive charge. So here's a nice neutral, non-neutral atom, and 2, 4, 6, 2, 4, 6, 8, 2, 4, 6, 8. Everything's obeying the octet rule. I could take a curved arrow and draw these electrons jumping that carbon. That put a bond there. Notice now it gives nitrogen its 3 bonds, which it likes. It has no charge. Nitrogen normally likes 3 bonds. Over here it's got 2. That's why it's got that negative charge. And here's oxygen with 1 bond, but they all have a complete octet. So there is the negative charge. Negative charge is a little easier to deal with thinking of electronegativity. The more electronegative atom is going to be the most pleased with the negative charge. Or we can say when both resonance forms obey the octet rule, the major contributor is going to be the one with the negative charge on the most electronegative atom. All right, now for some hands-on experience. Draw a detailed mechanism for acetic acid losing a proton to water, forming the acetate ion. Be sure to show resonance forms for the acetate ion. And you probably say, what is acetic acid? Well, we're going to play with Lewis structures, and we're going to play with condensed structures. There is a condensed formula for acetic acid. Hopefully you can already write a Lewis structure for water. So here's a good practice. In organic chemistry, nobody's going to sum up all the electrons and start this Lewis structure of acetic acid by summing up electrons and trying to figure out what the central atom is. We're kind of probably look at this CH3 and say, well, carbons like to form chains, and hydrogen can never bridge 2 atoms because it only forms 1 bond. So it must be a terminal element. So that's the front part of this molecule. There's another carbon. And now I got to put 2 oxygens on here. And I'm gonna help you all along and just say, I know where we're going. Now, I don't see any charges written on this. So obviously I gotta, maybe now's the time you'd sum up all the electrons and put some in. But this oxygen's happy and it's got 2 bonds. I'm going to just put those electrons on. Is this carbon happy? Now it'd be a +1 charge. It's only got 3 bonds. Is this oxygen happy? No, it only has 1 bond. So if I put a double bond there, I could be sloppy and just go on. All right, so if you went back to Chem 1 and you summed up all the valence electrons you got to work with there, you should find all of those down here. All right, so there is acetic acid. Here is my water. So now, how does an acid-base reaction occur? Well, in aqueous solution, water is going to act as the base, and it's the lone pairs on water. So I'm going to take my arrow and draw it grabbing that proton like that. And something's going to have to happen to those electrons there in that covalent bond. I'm going to draw those jumping back on to oxygen. Since I'm running out of room here, I'm just going to come over here. So there is my deprotonated acetic acid. Everything's obeying the octet rule, right? What about my formal charges? Well, this oxygen only has one bond. Oxygen likes to have two. So I got to put a negative charge there. So we get to draw a resonance structure out of this. Here is a resonance arrow. It's a arrow going in both directions, kind of like that. So I can draw these electrons jumping onto carbon, these electrons jumping onto oxygen. So the end of the molecule there is the same.
Wait, what happened to the hydrogen that was attached right there?
It jumped onto water. Yeah, so I'm gonna add that. And we wouldn't want to leave that out, and it's very interesting.
So should we put that arrow going the other way? Or no, I guess it's the same thing because it's one bond. Never mind.
Alright, so here's a reaction arrow. Here's a resonance arrow. Here's a curved arrow. Curved arrows show the movement of electrons. So now oxygen with 3 bonds has a positive charge, and acetate has a negative charge. Alright, so this is the conjugate base, and this over here is the conjugate. So there you have all the Chem 2 glory with acid base giving you a conjugate base and conjugate acid. You see the conjugate acid base pairs only differ by 1 proton. And now that we're into organic chemistry, you get to see the mechanism. This is a reaction mechanism. It has curved arrows showing shows an atom moving, that proton moving from acetic acid to water. We say acetic acid protonates water. Now we have the hydronium ion, and acetate is a polyatomic ion, and it comes from acetic acid. Any questions on this one? So you saw me in that example taking a CH3 and saying, oh, that's going to be a real common thing. We might call CH3 that is bonded to something else. Might think of a methyl group here and a methyl group here, and they're connected. That gives us ethane. So condensed formulas. You just heard me say that word before we did that exercise. What is a condensed formula? It's one written without showing all the individual bonds. Atoms bonded to the central atom are listed after each central atom. We have 2 central atoms. And a carbon chain can have many central atoms. But we're going to use our knowledge about carbon forming 4 bonds and filling in all the necessary pieces to make it work. All right, now pull out your piece of paper. And we'll work on these, and then I'll come around and look at your page. All right, so here's our condensed formula. We want to turn it into a Lewis structure. So there is a methyl group. Now we might even think to ourselves, well, I got 2 of these that I got to hook up to something. What are they hooked up to? Well, everything else over here, oxygen likes 2 bonds, hydrogen likes 1 bond, so it's going to be on the outside. So this carbon has the 2 methyl groups on it. So it doesn't matter how you do it. I'll probably just do it this way to give myself a little more room. All right, now what else? Now I go back to my rule. Carbon likes to form 4 bonds. I've given both these carbons 4 bonds. This carbon here presently only has 2. So I got to put a hydrogen on there. And I think I'm going to do something like this. So I brought in a model kit. So we're going to learn alkyl groups in a little bit. Here's 2 methyl groups. Here's that 3rd carbon. Of course, it looks like a methyl group. We're going to imagine hydrogens bonded here. So if I take that middle carbon, put a methyl group on it, take and put, so now I have the CH3, and the CH3 attached to this carbon. This particular model kit, red, it's going to stand for oxygen. And here's the hydrogen. So in my Lewis structure, I kind of have it drawn like this. So a beautiful thing about organic chemistry, or an annoying thing, I could have just as well drawn this. So sigma bonds can rotate. What does that mean? Sigma bonds can rotate. So there you see that sigma bond rotating, this sigma bond rotating, this sigma bond rotating. So in my structure, I kind of drew it this way. The first correct Lewis structure I saw one of you draw was more like this, and that's like my last structure down here. So same molecule, just different conformations. Now I've jumped ahead to about almost chapter 5. Organic chemistry is very visual. It's good to be able to visualize things in your mind. If you have a hard time doing that, there might be some challenges. All right, how about that bottom one? I threw a little curveball on that one. Since time is moving forward, and most of you got most of the way done with this, shortly in the future, you're going to look at this and go 1, 2, 3, 4, and you're going to just hook up 4 carbons in a chain, and then you're going to put your 3 hydrogens on each end carbon, these hydrogens there, then you're going to look at it and say, well, how do I get carbon to obey its rule of carbon liking 4? Carbon likes to form 4 bonds. And none of these had any charges, so we had to put them together in such a way that each carbon had 4 bonds. Oxygen obeyed the rule of 2. And if you're really bored, you could sum up all the valence electrons you would in a Chem 1 exercise and see that they're all there. But we got so many of these to do, we don't want to do that. And we want to get used to just seeing the structure. You want to be able to take a condensed formula and be able to turn it into a Lewis formula. Here's a couple more. All right, that was pretty good, except for the carbon with 5 bonds.
I put it on the wrong carbon. I got them mixed up.
So most everybody got to this point. All right, that's all. I'll see everybody.